when you're trying to draw carbons connected by triple bonds. So that's why they're straight. So any questions on the difference between alkanes, alkenes, and alkynes? No? All right. So let's see. What do you guys think this one is? Just, you don't have to name it, but alkane, alkene, or alkyne?
It's alkene, Kene. It's just a double bond.
Mm-hmm. This one's an alkene. What about this one?
Alkane,
Alkane. Mm-hmm. And this one?
Alkyne.
Alkyne. Good job. And this last one?
that one is a
Alkane.
alkane.
I believe it's a nickname.
Mm-hmm. That one's just an alkane. So we're only focused on these carbons and their connection to each other. So they're just connected through a single bond. All right. So yeah. So an alkane. So now let's move on to naming hydrocarbons. So the first thing we want to do when approaching any structure is we want to identify and count the longest carbon chain. So in this case, how many carbons is our longest chain?
It's 5. So pentane.
Mm-hmm. Yeah. And we know it's 5 because we're going to go like this, and we're going to use those 5. As opposed to starting down here, we could only use 4. So we know that that previous one was the correct answer. So 1, 2, 3, 4, 5. So like Chess said, what does 5 carbons indicate? What name?
Pen.
Mm-hmm. Pent.
So me peanut butter. Sorry, no, that's my bad. I apologize. I think I confused myself. But yeah, it's pen.
Yeah. Yeah, so me peanut butter, that's for the first 4, but we're at 5, so we're going to use a pent. So yeah, and then we can see that because there's only single bonds, what is our suffix?
Ane.
Ane, A-N-E. Mm-hmm. So we identified our parent chain, or the longest carbon chain, as pentane. So we can put that to the side right there, and we'll come back to it. The next thing we're going to do is name the substituents. So in this case, we have this CH3 sticking out. What do we call, what is our name for a carbon chain that only contains one carbon?
Methyl.
Mm-hmm. Methyl. So think about it, it's just one carbon all alone. When you're all by yourself, you would say me, like, I don't know, me was all alone. I don't know how to use it in a sentence all of a sudden, but yeah. So methyl is our name. And where is it? What carbon is it attached to?
3.
3.
Mm-hmm. So we could refer back to that number we had previously, and it's attached to the 3rd carbon. So what we're going to do is put 3 and then methyl. So we identify what it is and where it is. And so now we need to find priorities. So we have identified all the structures. We got them in the side right there. All we have to do now is figure out what order we put them in. So our parent chain is always going to go last. So we go ahead and put everything together. Yeah. So our parent chain is always going to go last or to the far right of the name. And then since we only have one other thing, we know that's going to be first. So we put pentane and then 3-methyl right behind it. So the name of this compound is 3-methylpentane. Not too bad. Any questions on this? Hopefully it's a little bit more clear. Let's see what I have next. So naming alkenes. So if we look at the empirical formula for these two down here, they're both C4H10. But how can we tell the difference between these two? We could tell the difference using the cis and trans method. So hopefully you guys are a little familiar with it, but this should clear it up if there's any confusion. So this one, I drew in the hydrogens, but this one is this one right here. There's no hydrogens drawn in on the left, but it's the same thing. So the first thing we're going to do when approaching this problem is you're going to want to draw a line through that double bond horizontally, just like this. And we're going to think, so let's focus on the left side first. What's heavier, this hydrogen or this methyl group?
The methyl group?
So the methyl group is heavier. So we're going to put a little star next to it. What about the other side? What's heavier, this hydrogen or this methyl group?
Methyl group.
The methyl group. So let's put a star next to that as well. So if they're on the same side, we're going to use the term cis. Cis means the same. You could tell it's a cis because it kind of makes like a C. So this one would be cis MEPB. What do we call a carbon with 4 carbons?
Tetra? No, sorry. Am I wrong? No. Damn it. Butane? Oh, butene, sorry.
Butene. So we know it's but. The presence of a double bond tells us we're going to use ene. Now, where is the double bond? What carbon is the double bond on?
It's on 2. It's between 2 and 3, so it's on 2. Yeah.
So it'd be 2-butene. Or you could also write but-2-ene.
Hey man, can you repeat how you got butene?
How I got
I'm
butene?
confused a little bit.
Yeah. So we know the presence of 1 carbon is meth something. 2 gives us Me. So methyl or meth something. And then 3 is propyl or prop. And 4 is but. And we know this is an alkene because of the presence of a double bond. So we would add ene to the end of it. And then we just have to write where the double bond is. So that would where the 2 is. And then we just add cis to the beginning. Cis 2-butene. Does that make sense? Any questions on this method?
Okay, yeah, I got it. Yeah.
Okay. So I'm going to clear everything. So let's try
Question, I'm so sorry.
Oh, no, go ahead.
This one, would it be cis 2-butene?
This one on the screen right now?
Yeah.
No. So we determined that this one was cis-2-butene.
Yeah, sorry. Is this one I'm talking about? I apologize.
Oh yeah. No, yeah. So this one is cis-2-butene.
Okay. Thank you.
And then, so this one, we already know it's trans, but let's go ahead and do the steps and see kind of why it's trans. So like before, we're going to draw the double line, the dotted line. And so what's heavier, hydrogen or this methyl group?
Methyl group.
Mm-hmm. So let's put a star next to it. And what about on this side? Methyl or hydrogen? So you guys already know methyl group is heavier. Mm-hmm. So let's put a star next to that one. So we know they're on opposite sides of the dotted line. And so we'll use trans to indicate that they are on opposite sides. So the name of this one would be trans to butene. And yeah, just like that, that's the difference between cis and trans. Any questions on the cis and trans thing? I think if you just use this method, it'll work out. Alrighty, let's see what I got next. Naming hydrocarbons, extra info. So a few things we want to go over is we want to make sure that when we name things, we're going to use the least numbers possible. And it kind of means when we add up all the numbers, it should be equal to the lowest sum. So let's say we have something like this. And we got a methyl group right here and a chloro group right there. Now, why wouldn't it be 1, 2, 3, 4, 5, 6, 7, 8? So would we want to put the methyl group on carbon 6 and the chloro group on carbon 7? And if not,
No,
how
from right side.
Mm-hmm. Yeah, so instead, what we want to do is approach it from the right side. So that way our chlorine is on carbon 2 and our methyl is on carbon 3. That way it's 3 plus 2 as opposed to 6 plus 7. And so the top one equals 5, lower one, some number higher than 5, 13 in this case. So we're going to want to write it from right to left. And that's kind of what that rule means. So we're always going to want to have the sum of the carbons to be the lowest number possible. Does that make sense to everyone?
Yes.
All right. Let's see. Next, I think I got some practice problems. So what's the name of this one? Pretty simple start.
So it'll be hexane.
2, 4, 6. Yeah. So we have, let's see. We got 1, 2, 3, 4, 5, 6. We have no functional groups. 6 indicates hex. We only have single bonds in this case. Hexane. We don't have anything to attach to it. It doesn't have any accessories, no substituents, no functional groups. So this one is just hexane. So this next slide, I believe, is blank. And I wrote down so I could use the iPad. So let's try some problems from the homework. So I'm only going to do odds from your homework. So let's try this one right here. This one is on page 76, number 7. I think you guys said was giving you some trouble. And that should be a 2. So who wants to try and give this a shot? What's our longest carbon chain?
So the longest one is 6. So, and it doesn't have any double bonds or triple bonds, so it'll be hexane.
6. I saw someone say 7. Why is it 7 as opposed to 6?
Because the thing in parentheses says 2. So I think there are 2 carbons there.
Mm-hmm.
See, that's what I didn't get. Thank you for explaining that. All right, cool.
Yeah. So basically what we could do for trying to understand this problem is kind of draw it out. So we got this structure down here connected to a carbon, connected to a second carbon, connected to our terminal methyl group. And then those carbons have hydrogens coming off of them, but I'm not going to draw them. So when it's drawn out like this, we can easily tell that our longest carbon goes from here, carbon 1, 2, 3, 4, 5, 6, 7. So it turns out our longest carbon chain is 7 carbons long. Let me get rid of those red ones. So what do we call a carbon chain with 7 carbons?
Heptane.
Heptane?
Mm-hmm. Heptane. So we have hept because 7 carbons. I don't see any double bonds, only single bonds, no triple bonds. So we use ane. But what about this guy down here? What's his name?
That's a methyl.
Mm-hmm. So we got methyl. And where is he?
We will put him on 1, 2, 3, 4.
3, isn't it?
Oh, 3, sorry. And come from the other side.
Is it on carbon 3?
Either way.
It's 4.
Yeah. So it's going to
carbon
be 4 either way. So let's count from the top. We got 1, 2,
Oh, yeah.
3,
Sorry, my bad.
4. That's okay. And then if we count from the opposite side, turns out it's also 1, 2, 3, 4. So the name of this one is 4-methylheptane. And yeah, that's number 7. I know you guys said you had trouble with number 10. So I'll draw it out for you guys, but I'm not going to do it for you. But you guys could help each other out, and I'll try to guide you in the right path. So we have an OH down here, and up here, that's some crazy looking thing. The circle indicates that it's that those triple bonds are present. I'll just draw the triple bond. I mean the double bonds. So, who wants to give a shot at this?
Let me try some. Now I know the OH means alcohol, right? So what I got was the longest chain was 7, so I know it will end with heptanol, Heptanol.
Mm-hmm.
That's what it will end with. And that little circle thingy with the single line, isn't that phenyl? Phenyl.
Okay, so we got a phenyl group.
But this is the part that gets confusing to me. Is it also methyl or is it just phenyl?
This one would just be a phenyl group.
Okay, thank you. That was the problem I was having. So if that's the case, so phenyl would be on 1, 2, 3, 4 in either direction. So that means it'll be 4 phenyl, 3 heptane.
So like this.
Yes, that's how I would put it.
4 phenyl, 3 heptanol. Mm-hmm. Yeah, so that's correct. And then when we put it all together, it'll be 4 phenyl.
Yeah, I'm getting
3
good at this shit.
yeah, heptanol. And yeah, just like that. Any questions?
How?
How? Alrighty, yeah. So,
Yeah, like he went too fast. I got lost.
okay, yeah. So let's go and start with our identifying the longest carbon chain. So in this case, our longest carbon chain. Do I have? No. So in this case, our longest carbon chain is 1, 2. Can I share the functional group name chart? Mm-hmm. So if you look in your workbook, on page, where is this? 66, it gives you some functional groups there. And also on page 64, it tells you like the prefix for all of your carbon chains. So I would definitely refer to that. And also, it's not in your workbook, but the halogens, so from fluorine down rather, those could all be functional groups as well. So F, fluoro, Cl, chloro, bromo, iodo, and then the rest you don't typically see. But yeah, we'll go over the functional groups in a little bit. And then OH.
Quickly, is it possible for us to go over 6, 7, I'm sorry, 6, 8, and 9 really quick? Or is that too much to ask?
No, we could definitely go over those. Let's get through this one real quick. So we look at this, we've identified the longest carbon chain. Let's get rid of this for now. So the reason we wouldn't count this one up here in our carbon chain is because it's acting as a functional group. That benzene ring, so something like this with a double bonds, drawn horribly. But whenever it's attached to something like this, then it's a functional group. Let me get rid of that. That's pretty ugly. But yeah. So we've identified the longest parent chain. So we could write it down. So 7, indicated by hept. And we only have single bonds. So when it's going to be heptane. So the next thing we want to do is move on and identify our functional groups. So like Chess said, let me get rid of these numbers right here. So like Chess said, this one up here is called a phenyl group. So PHENYL.
Yeah, I just got it. Like I was just missing the phenyl part, but
Oh, yeah.
I got it now.
So that's the phenyl, and we know it's on carbon 4. And this OH group down here, we know is an alcohol. And we indicate alcohols only by the suffix OL, and we know it's on carbon 3. So 3 something all. And where we put the all, we just drop the E, add the all, fill in the rest of this, heptan, put our 3 over here, and then add our 4. Not letting me put the 4. There we go. 4 phenyl. 3 heptanol. And we always want to separate our numbers from our letters using the dashed line. We will be using a comma soon in some of these. But yeah. So yeah, that's that. So let's go over number 6 real quick on page 76 of your workbook. So I'll try my best to recreate it. So we kind of got an OH going on up here, connected to a zig, zag, zig, zag, zig. That goes straight down, branches off like this, and like that. And then right here we have NH2. Alrighty. And just some things to highlight for this one. So NH2 is amino. Alrighty, so let's see. Who haven't we heard from? Melissa. What's our longest carbon chain?
I'm having a little trouble with my Wi-Fi, but
I think it's 7.
So Masha coming in to save the day. So 7. Oh no, you're good. I think Melissa was having some trouble. But yeah. So 7 is our longest carbon chain. And do we want to start counting from the top or from the bottom?
From the bottom left.
All right, so let's try counting from the bottom left. So we got 1, 2, 3, 4, 5, 6, 7. So when we count from the bottom left, our alcohol is on carbon 7, and this ethyl group right here is on carbon 4, and our amino is on carbon 3. So we add all those together, it comes up to 14. But let's try counting from the bottom, from the top rather. Let's see what we get. So we got 1, 2, 3, 4, 5, 6, 7. So if we count from the top, our alcohol is on carbon 1, our ethyl is on carbon 4, and our amino group is on carbon 5. And this adds up to 10. So in this case, we're going to want to count from the top. So that way we get a lower number. Does that kind of make sense? Mhm. Yeah. So in this case, we're going to want to start from the top. So we get that lower number. So let me erase all of this. And let's erase our red numbers. All right. So we've identified the longest chain as being 7 long. What do we call something that's 7 carbons long?
So it'll be heptanol.
Mm-hmm. So we got hept, and then we only have single bonds in this case. So we have ane, but we drop the E and add all to it. And our alcohol is on carbon 1. So we got heptanol, but we got some other substituents sticking out of this thing. So what about this one right here? I kind of already said it earlier, but what do we call 2 carbon long functional group or substituent? Ethyl.
Ethyl.
Mm-hmm. So we got ethyl, and it's sticking out of carbon 4. 4 ethyl. What about this amino right here? Well, I guess already.
Okay.
So we got amino. And where's it sticking out of?
Okay, I see where I was going now.
So it's sticking out of carbon 5. So now we're going to go ahead and just write them all together. So we have 4. Oh man, that's a nasty looking 4. 4 ethyl, 5 amino. Oh, oops. Oops. And then 1.
Amino 4 ethyl because of the alphabetical order.
Alphabetical order. I'm glad someone caught that. Oh man, I don't know what's going on with my writing. But yeah. So like who was that? Leslie? So like Leslie said, I believe, we're gonna want to put them in alphabetical order. So we know this is our parent chain. So this one has to go last. So you could go ahead and write that. Heptan all. But when we're deciding between this one and this one, we're gonna want to write them in alphabetical order. So in fact, our amino is gonna go first, and then our ethyl. So at the end of the day, we have 5 amino, 4 ethyl, 1 heptanol. And yeah, does that make any sense? Did I lose
Yeah.
anybody anywhere?
I have a question though, Marco.
ahead.
So when would it be methylamine? Because that's where I went wrong. So what I initially put was 4 ethyl, 5 methylamine, 1 heptanol.
So methylamine. So I'm guessing you think that there is a carbon at the end of this, like that, right?
Yes.
So that in fact would not be the case. If there was let's say there was a bend like this, and then it had the amine right there, then we would see that there was a carbon right here, and then it kind of bounces off, and then it goes to the amine. But in this case, just like this one is connecting directly to the oxygen, this bond indicates a connection from this carbon to that nitrogen.
Thank you so much. That explains a lot, because I think that was my issue. When I see the line branching off, I thought methyl goes in front of it. And I know when methyl goes in front of it, it changes from amino to amine. So it has to have that additional line, right? For it to be that, from what you explained.
Yes,
Okay.
I'm understanding
Got
you
you.
correctly.
Got you. Yeah.
But yeah, so someone asked, why did amino go first? And I think Pablo clarified, because it starts with A comes before E, so amino goes first, and then our parent chain always goes last.
Oh, okay. Thank you.
Yo, how did we choose which chain to use? Because I saw that you have like 3, I think. So I got a little bit lost in there.
Yeah, so when identifying how long we want our carbon, our parent carbon chain, we want it so we have the longest, but also the lowest number. And I'll kind of clarify that. So let's start from the bottom real quick. So we've identified our longest carbon chain to be 7 long, and it follows this pattern right here. So we're going to try and number it. So 1, 2, 3, 4, 5, 6, 7. And on the other side, let's do 1. Oh, I don't want the same color. Let's do 1, 2, 3, 4, 5, 6, 7. So when we look at the red numbers, we see our alcohol is on carbon 7. We see our ethyl group is on carbon 4. And we see our amino group is on carbon 3. So what we want to do is add up all of these numbers, and they add up to 14. And we're going to do the same for the blue. So I'll quickly say alcohol, carbon 1, ethyl, carbon 4, and our amino is on carbon 5. So we're going to add those up as well. And in this case, they come out to 10. So we're going to use whichever order gives us the lowest number. In this case, we're using the blue numbers. So we could get rid of our red numbers and use these blue numbers to help us identify where things are. And then you can leave, obviously you're not gonna have blue numbers, but you can leave those numbers up while you go ahead and solve through this problem.
Okay.
Does that kind of clear it up for you?
Yeah.
All right. Very good. Alrighty. So I know we wanted to go over some more, but let's go ahead and move on because we do have a lot to cover. And I did want to do a lot of practice problems because I know you guys' exam is on Monday, Wednesday, next week.
It's all next week.
It's on Monday, but I think he gave us, we have up to 3 chances, I think, for the entire week.
Yeah, the whole week. Yeah,
Yeah.
Monday through Sunday.
Alrighty. So yeah, let's go ahead and get through everything here, and then we'll go ahead and do some practice problems. So I'm going to clear the screen. All right. So functional groups, additions to hydrocarbons, kind of like accessories. So yeah. So what do we call something that goes around our wrist? Just a little band. It's not a chemistry question.
A ring? I don't know. I don't know.
We call it a bracelet, right? Or
Bracelet,
a wristband. So we got bracelets. And what do we call something? What do we cover our feet with?
Anklets?
You cover your foot with an anklet?
I don't know. You're talking about bracelets.
Socks?
With socks. Yeah, so we cover them with socks. So let's say we have a bracelet as opposed to a sock. That's a very large sock. But we can tell the difference by how they look. And that's kind of how we're going to identify our functional groups. Man, all that sounded better in my head. But yeah, we just look at functional groups and we name them. Yeah, honestly, forget all that. So it says, moving on page 64 of the workbook, we got some prefixes for naming carbon chains. We add YL to them if there are substituents, as opposed to the parent chain. Example, methyl, propyl. What do we call this right here? Do you guys know?
ISO.
Iso what?
Isopropyl.
Isopropyl. So iso meaning the same on either side. And there's 1, 2, 3 propyl. So this is called isopropyl. And that's that functional group. And page 70 gives you some more functional groups that must be remembered. Functional groups, for the purposes of this class, you mainly just need to be able to identify them and tell me their names. So some examples here, and we'll get into these examples into a little bit more detail. And like I said, these should be on page 70. Yeah, on page 70. So I believe I did the first 4 or 3. The rest I didn't make any PowerPoint slides on because I was too lazy to. But they kind of all follow the same rule. The amide and the amine kind of follow the same rule. And the rest you guys should be familiar with. I think I covered ketones. If I don't, I would like to. So the first one we're going to look at is the carboxylic acid. It is, we identify it when we write it as oic acid, and an example is ethanoic acid. So what is eth? What does that indicate? If we're trying to draw out ethanoic acid.
2.
2. So we got 2 carbons. And we know that there is a carboxylic acid functional group attached to these. So we kind of follow this right here. So R is just the rest of the carbon chain. But in this case, there's just 2. So we add this right here. And just like that, we have ethanoic acid. Anybody know the common name for ethanoic acid? Acetic.
Acetate. Yeah, acetic acid. Sorry.
Yeah, acetic. Did I say acetic? Acetic acid. So just a rule of thumb, whenever we have two carbons, is acete something. And then whenever we have one carbon, it is form something. So if we had just a carbon like this, what do you think the common name of this one would be?
Formaldehyde.
So we have
Right.
this carboxylic acid.
Sorry, I'm thinking about something else then.
Yeah, I
Sorry.
think you're thinking about something else.
Yeah, sorry.
But yeah, you're right in your thinking, but this one would just be formic acid.
Oh, okay, thank you.
Do you guys know where you can find formic acid? Antibiotics. Some trivia. You can tell your friends. Or not. You probably sound a little lame, but yeah. So carboxylic acids. That's them. Any questions on carboxylic acids? How to identify them? Really, you're just looking for this carbonyl group attached to an OH group.
Question, Marco. Now I get when it has one carbon, it starts with form. How do you know to add ic to it so that we know it's formic acid?
If there's the presence of these functional groups. The reason it's not formanoic acid is because that's not what the chemists, is that a word? The chemists, that's not what the chemists of old called it. They called it formic acid before they knew how to use before they came up with IUPAC naming, standardized naming. It's kind of like an answer, but not an answer. But I mean, that's just what it's called.
No, I get it. Thank you.
Yeah. Alrighty. So let's see what we got next. So esters. Esters are fun. So esters we name with alkyl plus alkyl OH. So an example in this case would be propyl pentanoate. So you can see I kind of color coded it. So what we want to do is draw a line in between the two oxygens. And the oxygen with the double bond, so this one right here, we're going to use as our parent chain, kind of parent chain. So it's going to be the one that gets OH in the end. So in this case, we have 1, 2, 3, 4, 5. So we got pentane, OH. And then we just add the rest. So this one has 1, 2, 3. 3 we indicate by propyl pentanoate. And that's kind of a good way to approach naming esters. Yeah, just cut down the oxygens. Whichever one has the double bond in, it's going to get OH. So any questions on esters? How to identify them? Esters always have that carbonyl group connected to an oxygen, connected to a carbon chain.
I'm not gonna lie to you, I'm kind of lost.
No, it's all right. It's all right. So this is kind of the cookie cutter ester. So we have a carbon chain coming off of the R's indicate carbon chains, if you guys didn't know. So yeah, what's confusing you, Che, about this? Like the naming part, or just like identifying an ester?
identifying an ester is the
Mhm.
problem right now.
So we know it's an ester because, so we're going to look for this carbonyl group. And a carbonyl group is just C attached to a double bonded O. So we have the carbonyl group. And also attached to the carbonyl group is this single bonded O. And that single bonded O is also connected to another carbon chain. So when we see a carbonyl group attached to an O, further attached to a carbon chain, we know that it's an ester. And yeah, that's just something you have to practice on, I guess. But yeah. So can you guys tell me the difference between an ester versus an ether? Do you guys know?
The ether only has one oxygen.
Mm-hmm. So an ether looks like this. So only one oxygen. So 2 carbon chains, but only one oxygen. And there is no presence of a carbonyl group. And there's I like to remember it with this special little way. So so an ester has 2 oxygens. So we could kind of name it like, oh, that's this this oxygen right here is named Esther. And like Esther is a nice name. So she has another oxygen friend. But this oxygen is named Ether. And Ether's an ugly name. I've never heard of anybody with the name Ether. So Ether has no friends. So it's all by itself. That's how I like to remember it. Esther, nice name. Has a friend. Ether, to the side. So yeah, you guys can use that if you want. It helps me out. So yeah, let us go to the next functional group. I think I have a practice. So yeah, let's try naming this one. So I color coded it for you guys so it follows the rules of the previous one. So we know our orange is going to be our parent chain and our blue is going to be our addition. So what's the name of our parent chain?
It'll be heptane.
1, 2, 3, 4, 5, 6.
Oh, hexane.
Mm-hmm. So someone wrote Delian. I don't even know if I'm still saying that right. Delian.
It's okay.
Delian. I don't know. Yeah, so hexane 08. And what about on this side? What do we call that? Maybe this helps out.
Methyl.
Mm-hmm. Methyl. Methyl hexanoate. Oh, oops. So yeah, this one is methyl hexanoate. Any questions on naming esters?
I feel smart. I get it now. I get it.
So if it would be another, like, let's say another carbon chain on the H3, what is it, H3C?
Mm-hmm.
It would be ethyl,
Yeah, so if it was like this,
Yeah.
it would be ethyl.
Okay. Okay, cool. Thank you.
Can you
Mhm.
count how you got 6
Yeah.
on the second
So
one?
we're going to start at the carbonyl group. So we know that there's a carbon right here. So that'll be carbon 1. Carbon 2, 3, 4, 5, and 6.
Okay, got it.
I know, like, when I was first approaching these, I was like, do we count that first carbon? Do we not? But yeah, we count the first carbon. Mhm. All right. In that case,
So the longer chain is always the parent chain in a situation like this?
in a situation like this, anything inside this orange box is the parent chain. So anything from the carbonyl group onward is the parent chain.
Gotcha.
Let's say it was drawn like this. We would still cut it down the middle, and anything from the carbonyl group this way is the parent chain. So whichever side has the carbonyl group. Mm-hmm. All right. And then I just wanted to clarify, H3C is the same thing as CH3. The reason I drew it H3C is because if I kind of drew it like this, I don't want anyone to confuse, like, oh, it's attached to the hydrogen and then attached to the carbon. But yeah, these two are the same. Just wanted to make that clear. All right. So the next functional group we're going to go over are amides. So amides are kind of fun, kind of not fun. Once you kind of get the hang of them, they're not all that bad. So we indicate it's an amide by the suffix amide. So let's look at this first one. They're all drawn at the bottom, but I'm gonna go ahead and redraw them. So propanamide. So if we saw this, the first thing we're gonna want to pay attention to is that prop. What does prop mean?
Three carbons.
3 carbons. Mm-hmm. So we draw 3 carbons. And we have AN, meaning it's an alkane. So we know that there are no double bonds and no triple bonds. And finally, we have amide. So amide is our nitrogen that could be attached to, is a carbonyl group attached to the nitrogen, which may or may not be attached to, that's supposed to be an R, that may or may not be attached to other carbon chains. But because we are lacking any other information, we could just assume that it's just our carbonyl group attached to our nitrogen. In this case, it'll be NH2. And that is an amide. Not to be confused with something like this, NH2 there. Because there's no, what's it called? Carbonyl group. It's lacking a carbonyl group. This is just amino. That's our amino functional group. So let's get rid of that real quick. Oh, oops. So that's our propanamide. So let's look at this second one. N-methylpropanamide. So we kind of tell that prop, 3 carbons, anamide, Alrighty, we know that there's an amide group. Got a nitrogen right there. And we also see that there's N-methyl. So what do you guys think that means? We have a methyl group. Where is it attached?
So it's attached to the end, so there's an extra line there, right?
Mm-hmm. So we got a methyl group sticking out of the N. And our nitrogen is going to be attached also to another hydrogen. So this is N-methyl propanamide. So instead of using like a number system, we're just indicating that there's a methyl group attached to our N. And if this was a 1, 2, 3 propyl, we would say N-propyl propanamide. And just use the same kind of nomenclature we've been using up until this point. But now let's look at that third one I have written down, NN-dimethyl propanamide. What do you guys think that one is? Does someone want to try drawing it?
I think I could give it a shot, maybe. I don't know.
Yeah,
I think it's going to be very similar to the one that we just did, except it's going to have an extra CH3 because it's dimethyl.
Mm-hmm. So we have our N. This is what we had before. So N-methyl propanamide.
Mm-hmm. So could I draw the extra line? Well, I don't know how to do it from here, but
I think you go to the top where it says options or more or something like that. And you just want to select annotate.
Options, more, annotate, no, text, shape.
We're just looking for annotate.
No, that's not it. Okay, I think I see it. So would it be, if I'm drawing it, okay. So if I'm drawing it, would it be like, I could do one there?
Yeah. So we add just another methyl to that. And because we have two methyl groups, we're going to clarify it's dimethyl. And yeah. Not too hard once you kind of just think about it, really.
I have a question.
Go ahead.
Why is it NN? Like, is it because it's attached? The methyls are attached to both of them.
So it's NN because so we see dimethyl. So we have two methyl groups. So we need to identify where each methyl group is separately. So one methyl group is attached to N. The second one is also attached to N. It may be redundant, but that is the system that we use.
Okay, thank you.
I guess the only question I have is, what was the difference with the N-methyl propanamide that it had a hydrogen attached to it? What was the difference? That one had a
So
hydrogen.
the reason it has a hydrogen attached is because it's also not drawn, but there is if we go out and draw the Lewis structure, there's also a lone pair right there. And the reason we had a hydrogen, like in this case, is because, let's see if I can draw it. So pretend that lone pair is attached to nitrogen. Nitrogen, we know, is part of the FON club, FON. So it wants to have an octet. So if we were just to draw it like this, and let's include the lone pair, it only has 6. So it just picks up a hydrogen to complete the octet.
Got you. Oh, all right. I see what you're saying now.
And then as we add the carbon chains, we just replace the hydrogens. All right. Any questions on amides? All right. I guess there are no questions. Let me see. I think I gotta. I don't think I could clear mine. Clear your guys' things. All right. There we go. Oops. All right. So amides. So now let's look at combustion. Now we're moving on to some organic reactions. Combustion was covered in Chem 1. It's when any hydrocarbon reacts with oxygen to produce carbon dioxide and water. So it could be an alkane, an alkene, or an alkyne. All of them, when they react with oxygen, will produce carbon dioxide and water. So I've written this one out, and I want you guys to try and balance it. Yeah. So go ahead and try balancing this reaction. I will do the same because I actually don't have the answer. So let's see. All right. I got the answer. What do you guys think? I'll give you a minute. I'm gonna go get some water real quick. Gotta stay hydrated. I will BRB. All right. Anybody got the answer yet?
I think
4O2, 4O2 on the left, 2 CO2 on the right, and 4 H2O on the right.
So 4H2O, and then you said 4O2?
4 O2, yeah, 2 CO2, and 4, yes, that's it.
Right. What do you guys think? Do you agree?
yes.
No, isn't there 6 H's on one side and then there's 8 on the other side?
So right here we have 6 hydrogens, whereas on this side, our hydrogens add up to 8. So our hydrogens are not balanced. So, does anybody have a different answer that they want to shout out?
Is it 2, 5, 2, 6?
2, 5, 2, 6. All right, let's go through it. Are our carbons balanced?
No, just kidding.
No, they are not. Anything else?
I think it's 2, 7, 4, 6.
2, 7, 4, 6.
I got the same thing.
2, 7, 4, 6. That is what I got. So let's go ahead and do this step by step. So the first thing I like to start with are the carbons. So on this side we have 2 carbons. On the right side, we need 2 carbons. Now we move on to the hydrogens. On one side we have 6. The other side we only have 2. So we're going to want to draw a 3. So now our carbons and hydrogens are balanced. So the next thing we're going to want to look at are the oxygens. So how many oxygens do we have on the right side as of now?
5, and I like to keep it at an even number, so we know that wouldn't work. So we got to change that 3.
So do we have 5? Don't forget this is O2 right here.
We have 7 actually.
7. My bad.
So on the right side we have 7. So because we have 7, we could draw it as a fraction on this side. So 7 over 2. And then this 2 will cancel out this 2. So now we have 7. But we don't really want to have a fraction. You can't have a fraction of an atom. So what we're going to do instead is multiply everything times 2. So this changes to 7. This changes to 2. This one changes to 4. And this one changes to 6. And just like that, everything is balanced. Any questions on balancing this? Just take so much of practice. Just a heads up. If you have an organic or a hydrocarbon that starts with C2, C4, C6, anything where C is an even number, you're going to want to double the carbon. You're going to just basically want to draw 2 right here as a rule of thumb. I'm pretty sure. So if we had CH4, yeah, you go ahead, Masha. Plus O2. Oh gosh, what is that error? Goodbye. Yields CO2 plus our water. We could check for my shortcut. So no, there is not a even number, so we don't have to double anything. So we should just be able to put a 2 right there, and that should be it, I believe. So yeah, if there's an even number, double it. So yeah, that's combustion. Now let's look at halogenation. So halogenation is when a hydrocarbon has some of its hydrogens replaced by a halogen. That's halogenation. So I kind of drew it out for you guys with methane here, but it could happen with any hydrocarbon. So this Br swaps places with hydrogen. So it becomes methyl bromide or bromomethane and HBr. And yeah, that's halogenation. Any question on halogenation? Let me see what it says. Yeah, that's halogenation. I guess let's go to the next one.
I was going to ask you. Oh, great. Never mind.
Oh no, go ahead.
I was going to ask you if you could explain that image one more time for me. The last one that we just did.
This one right here?
No, when you started with the halogenation. Yeah.
Okay. So yeah, these Br, that's kind of what that molecule looks like, just two Brs connected to each other.
Mm-hmm.
So this one is gonna swap places with this hydrogen. And yeah, that's about it.
So it's pretty much just swapping places with the hydrogen.
Yeah.
Okay, I got you, because I was confused by that.
Yeah, no. Don't think about it too much. It's just switching places. So now we're going on to reactions of alkenes. So these are reactions that involve double bonds, usually breaking them. In this case, only breaking them. So the first reaction that goes through in your workbook is hydrogenation. Hydrogenation. So when you see hydro, what do you guys think of? What element? Hydrogen.
Water.
Yeah. Kind of water, not quite. Don't get confused. It's not water. So hydrogen. Yeah. So basically what we're doing is hydrogenating the double bond. So these two hydrogens, kind of looking like this, are gonna show up. One of them is gonna go to this carbon. The other is gonna go to this carbon. And I kind of color coded it so that you can kind of see the double bond will break, and now the carbons will be having something like this. One electron will go here, one electron goes here, and these hydrogens come in with their own electrons to create some bonds. And it ends up like on the right side. And yeah, that's hydrogenation. Introducing hydrogens to a double bond in order to break it. Does that make sense?
Yes, it does make sense.
All right. Yeah, some of these.
I'm sorry, because if we, so say for example, we had that same image, but instead of it being plus H2, is it possible to do plus H4? would the bond still break, but we'll have 2 additional hydrogens, right?
Yeah. So let's say we had H4. So we know hydrogen can only make one bond. So in order to say H4, we just have to say 2H2. So let's say we have 2H2 on this side, and on this side, we would just have an additional H2. Really, we could cancel out one of them. And it just simplifies to H2. Hydrogen doesn't make H4.
Understood. Got you.
Yeah. So I'm going to clear this. So yeah. The next one we have is hydrohalogenation. So the introduction of, in this case, HCl, so a hydrogen attached to a halogen. And we get specific outcomes. You may be thinking to yourself, why is it H on this side and Cl on the right side? Can't it also be Cl on this side and H on this side? The answer is no. And the reason it has to come out this way is because of Markovnikov's rule, which is defined on page 72. Which is basically, there's a ton of words there, but I'll simplify it by the rich get richer. And what do I mean by that? So what I mean, we're going to pay attention to the hydrogens. So let's look at this carbon structure on the right. So of course, since we're dealing with an alkene, we know we're going to be dealing with a double bond. So let's look at this carbon right here. How many hydrogens does it have attached to it?
Two.
2. So let's go and write that. What about this one right here? How many hydrogens?
1.
1.
1. So which one would you say is more hydrogen rich?
The first one.
The first one. It has 2 as opposed to 1. So we know because of Markovnikov's rule, the rich get richer. So the hydrogen rich carbon will become more rich in hydrogen. So it's going to want to move over to this one and make it CH3. And the chlorine will just move over and go to the CH. And that's Markovnikov's rule and hydrohalogenation. So yeah, I hope that makes sense to everyone. Does everyone kind of understand Markovnikov's rule? So let's say we had
Yes.
something like this. Would it turn into, and let's say we're adding HCl again. Would it turn into this or this?
We'll turn into the second option.
The second option being the bottom one?
Yeah.
So we turn to the bottom one because this one has 2 hydrogens, 1 hydrogen. So our hydrogen is going to move over here. Our chlorine move over there. Now let's say we have something like this. What happens now?
Interesting. I don't know.
Yeah, so they're both equally as rich, or I guess equally as poor in this case. So it's kind of a coin toss. Either one is likely. Yeah. So this one, oh, oops. It's just as likely as this one. So yeah.
So that one doesn't just lose the double bond and that's it? Like, it still looks the same?
Yeah, so it'll look the same. This one right here kind of looks like this. And then when we break the double bond, so the double bond will break, but we still have 3 carbons. So we're still going to have this type of formation, conformation. And we'll just add the chlorine right here. So yeah,
Gotcha.
the shape won't really change. Just break the double bond, figure out what goes where, and just redraw it.
So the formula for the right side would just be C3 ClH7 H7.
Mm-hmm.
Okay, cool.
C3, H3, 4, 5, 6, 7, and Cl.
Okay, so it's the Cl goes after, or does it matter?
I think it technically is CCl H7. I think it goes in alphabetical order.
Okay, cool. Thank you.
Mm-hmm. But so I just erased it. One way that chemists and a lot of your textbooks, a lot of online resources will have all of this written out. And that's a good point. I forgot to mention this, but so they kind of break it down into sections. So they will write CH3, C, H, Cl, CH3. And they write it this way because that's kind of the order in which it goes. So we have this methyl group, so our CH3, followed by a carbon that's attached to a hydrogen. So we have CH, which is also attached to a chlorine. So we have that H and Cl right there. And we know all the carbons are kind of connected to each other. So it'd be followed up by another kind of methyl structure. And that's why in that one problem, it was CH2, 2. It kind of indicates that there's C surrounded by hydrogens connected to another C surrounded by hydrogens. So either C3H7 Cl or this up here, they're both correct. But this one kind of helps you visualize it, if that makes sense.
Yes, it does. Thank you.
Mm-hmm. So let's see, what do we have next? Halogenation. So this one, similar to hydrogenation, but with halogens. So the difference between this one and the halogenation from before is the presence of a double bond. So because we have a double bond and we know we're working with reactions involving double bonds, the first thing we're going to do, obviously we know we're going to break the double bond. And now the carbons have their electrons. So it's going to break apart this bromine, Br2, and just move them each to their own carbon. And that's how we end up with this on the right. So similar to hydrogenation, just involving halogens. So yeah, not too complex. Don't overthink it. Just remember, break the double bond, add whatever you need to add, And yeah, let's go to the next one. So condensation, and this is reactions between functional groups. So condensation is between two alcohols to form an ether and water. So alcohols, we know OHs. I kind of color coordinated it, so it kind of makes more sense. So you can see where everything's coming from. Two alcohols will combine, dump the OH and the H in that case to form H2O. And you kind of just want to connect the lines. So we got an O, and we just have that second line. And that's how we get this ether. And I guess quickly, we didn't go over it, but naming ethers, we want to say oh man, what's it called? So the suffix, so this one is H3C, this one is the same thing, so CH3. So since there are only methyl groups, we're going to call it dimethyl ether. And let's say we had something like this. This one would be, this one has 2, this one has 1. 2 we know is ethyl, and then methyl ether. That's how we name them. Nothing too fancy, just say them and then follow it up with ether. But yeah, any question on condensation? What about naming ethers? Any questions on naming ethers?
Where in the page 70, it says something about oxy. What does that have to do with?
Yeah, the oxy is so it's ether okay, yeah. So oxy on the substituent. So I believe what it's referring to as when it says oxy. So let's look at the ethyl methyl ether. Name substituent plus ether. Okay, yeah. So let's look at this one again. So with that other version of naming ethers, we're going to look at the longest chain. In this case, it'd be the ether. So our methyl would be our substituent. So it would be methyl ethoxy. Yeah, you could name it like that. I'm not too sure about the oxy thing, but the way I previously told you, where it's ethyl methyl ether, that's also correct. I prefer using that one. There's probably a video online you could find about naming ethers that might go into the ethoxy or the oxy method. But I think it's easier saying ethyl methyl ether. And I guess if you look both of them up, you should come up with the same chemical thing. Chemical.
Thank you for that.
Yeah. So I guess it's up to your preference. I'm not too sure what he'll have on the exam. But yeah. Alrighty. So I think we have one more reaction. So this last reaction is a reaction between an alcohol and a carboxylic acid. And this will give us an ester and water. So once again, I kind of colored some things so you can see where the water comes from. So whenever an alcohol and a carboxylic acid meet, the alcohol will drop its OH, pick up this hydrogen to form water. And what is left of is this methyl right here, and that methyl is just going to attach where that hydrogen previously was and form an ester. And yeah, so we could have something crazy like this plus our OH. And when we're going to want to see what it's going to look like finally, we just kind of want to count how many carbons are on the alcohol. In this case, 1, 2, 3. So we just redraw this without the hydrogen, and we just attach 3 carbons. And yeah, that is alcohol plus carboxylic acid.
So just to understand this properly, when I'm looking at the first thing that you got, the H2O is by, no, I thought you broke the double bond to get that. So how did we get, never mind, I think I see it now. Never mind, I got it.
Mm-hmm. So remember, these are reactions between functional groups. So typically we're not breaking double bonds to oxygen. Yeah. Any questions on anything that we've covered so far? I think that's all I have planned on this PowerPoint. Yeah, I think that's my last slide.
Marco, question. So the CH3, so in order for you to add H2O to the alcohol, you need to add a methyl group in there? Because isn't that methyl, CH3?
Mm-hmm. So this right here is kind of OH. It's supposed to It's supposed to represent. So this is a methyl group right here. Is that what you're asking?
Yeah, I was confused of where the methyl group came in from. So you're saying that there is a O because the line, that is a methyl group right there. I got it.
Mm-hmm. Yeah, so there's a carbon on one end and then the oxygen on the other end.
Thank you.
Mm-hmm. Yeah. Any questions on anything that we've covered so far? I think this next slide is just homework. So module 3, evens. So I'll include that. Evens.
Hey Marco, do you mind if I ask you one quick question? So if you have a situation like the homework that we had to do, if you have 2 lone pairs on a central atom, right? Would those 2 lone pairs be an additional region? So for example, which one was it? I'm sorry.
So something like this?
So if I have number 6, for example, the ethyl alcohol.
Number 6.
Is that the one? It's module 2 homework.
Module 2 homework.
So would that be 6 regions, or would that actually be, because I thought it would be 6 regions, or would it be 4 regions?
So ethyl alcohol. That's a weird way to name it. So ethyl, something like this. Ethyl alcohol. For the following molecules provide molecular formula, Lewis structure, resonance, electrochemistry, hybridization of central atom. So I'm guessing in this case, this one right here would be our central atom. And so that carbon is attached to another carbon attached to an oxygen, to a OH group.
Yeah.
Now, don't forget, whenever there is nothing else drawn, we assume that the carbon fulfills its octet by attaching to hydrogens.
Mhm.
So in this case, there would be 4 electron densities.
Oh, because do you mind if I show you what I did?
Go ahead.
Let me just draw it out really quick. Where's the option? Annotate.
Ethyl alcohol.
So this is what this is what I did. Try to so what I did was C.
Excuse me.
That's what I did.
Mm-hmm. Yeah. So
Is that the same thing?
it's the same thing, yeah. So it's not drawn, but this oxygen also has some lone pairs of its own.
Mhm.
But I think for the purpose of the homework, it's asking for like this structure, like right there in the middle.
Oh,
So we could identify like this carbon as the central atom. So you could
I
identify like
got you.
its bond length
When I,
and all that jazz.
because when I was counting the regions, this is what I did here. So that's 3, 4, sorry. And then I did 6. So 1, 2, 3, 4, 5, and then 6. So I couldn't figure out if it was 4 regions or 6 regions.
Right.
In order for me to figure out the shape of it. But what I ended up putting was tetrahedral for the EG, and for the MG, I put tetrahedral also in a bond angle of 109. That's what I put.
That I don't know the bond angles off the top of my head, but yeah, it would be tetrahedral because of
Okay.
that central carbon having the 4 sticking out of it.
Okay. Thank you. I appreciate it.
Mm-hmm. Yeah, I guess any questions from any of the modules? I won't see you guys until post-test. Or maybe after test. Or pre-test. If you take it Friday night. If there are no questions, we could go over some practice problems. Let me see. Let me clear all. Stop sharing. Share screen to the whiteboard. Share. All right. So let's do some practice problems. I'll take these practice problems from your Module 3 homework. I'm going to do the odds. So let's see. So let's look at number 9. I know you guys asked about number 9. Page 76. So number 9 is like that. Boom, 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 boom. And a 2. Right. So let's see. What's our longest carbon chain? Or I'll just ask you guys. What do you guys think the name of this molecule is?
I have 2 fluoro, 3 methyl. No, sorry, I'm looking at it wrong. It's 2, 3, 4 trimethyl, 1 nitro, cis 3 pentane. I might be wrong as hell, but that's what I got.
I could tell you that there were some right parts, but don't forget that there's no carbon here.
Okay.
I know that was confusing, but we cleared that up. So there's no carbon there. So what about someone else? Well, what's our parent chain? Let's start there. It's our longest carbon chain. 5. Mm-hmm. So, and it could be 5 either way. Well, let's see. Do we want to start from the left or from the right?
Because of the double bond.
Mm-hmm. So I think from the left I heard. 1,
Yeah.
2,
From the left.
4, 5. So we're going to name it like this. So we have our parent chain, pent, and we have a double bond. So what do we want to put after pent?
Ene.
Ene. Mm-hmm. So we have our parent chain. Now let's look at our substituents. What do we call this one right here? Well, actually, let's take a step back real quick. So we have the double bond. So we have pentene, but where is the double bond? We need to label that.
Double bond is on carbon 2.
Carbon 2. 2 pentene. All right. So now we go ahead. What is this group right here? What do we call that?
Methyl.
Methyl. Correct. So methyl. Which carbon is it on?
2.
2. 2 methyl. What about this one?
Methyl. 3 methyl.
3 methyl. 3 methyl. And what about that NO2? What is that called? Does anybody know?
Nitro.
Nitro. Mm-hmm. And which one is that one on?
That one's on 4.
4. Correct. So 4 nitro. So now we have everything. We've identified our parent chain and all the substituents. So now we need to come up with our priority. So we know our parent chain is going to go last. Yeah. So we'll put this 2 pentene. So what's going to go first, nitro or methyl? And why?
Methyl because alphabetical order.
Yeah. So L, M, N, O, P. So methyl is going to go first. So we're going to write our numbers, 2, 3.
Di.
And what do we put after that?
Dimethyl, because it's 2 of them.
Mm-hmm. Dimethyl. And then we'll add our 4 nitro, 2-pentene. And yeah, so we have dimethyl, indicating we have 2 methyl groups. And we identify where each one is, 4-nitro, 2-pentene.
So I
Any
have
questions?
a question. Why doesn't it have a cis in there?
Oh,
Because
true.
I was looking at the shape, and maybe because I was looking at the shape of it, that's why I thought it had.
Why does it have cis? I'm not too
No,
sure
I'm
why you
I'm
wrote
saying
cis.
why doesn't it? Yeah. So
So
because
let's try and do our little thing. So we draw our dotted line. What's heavier? This right here, or this on the bottom?
the one on top is heavier.
The one above. Let's add our star. Now what's heavier? CH3 or CH3?
They're the same.
They're the same. So cis and trans won't really work in this case. So if you were to write 2,3-dimethyl-4-nitro-2-pentene, that will be the correct answer.
Got you.
Cis and trans don't really apply to this one.
Okay. Thank you.
Let's see. Let's jump to another problem. Or does anybody have a problem they want to say? It's already 10:30, so if you guys want to go, you're free to go. I'll probably stay on for maybe another 10, 15 minutes. If you guys want to ask me questions, throw some problems out there from any of the modules. Yeah. But yeah, officially, you're free to go.
Could we go over, since you say you're doing the odd numbers, could we do some of the drawings
The
from
drawing.
on page 75?
Page 75, some drawings. Yeah. Alrighty. So let's look at number 3. 4-chloro-2-octine. Do you want to volunteer to draw it? Give it a shot.
Sure. I'll show you what I drew. I've been wrong a lot, but let's try. So I have 1, 2, 3, 4, 5, 6. Let me see. 1, 2, 3, 4, 5, 6. 9. So I put CL. And then 2. I apologize if I'm wrong, but that's
I don't know. You don't got to be sorry for being wrong. So, for those of you who are left, what do you think? Does this look right?
The triple bond is on the other side. So it's a bond, the line, and then a bond. Does that make sense?
Can you draw? It didn't really make sense to me. A bond, a line, then a bond. Oh yeah. Yeah, that would it looks a little prettier. But what does someone else have to say? Any other comments on this? I'll tell you,
said
Chet, it is technically correct.
the triple bond needs to be like straight or something like that.
The triple bond needs to be straight. So if the triple bond needs to be straight, yeah. So you're right about this beginning part. But don't forget, because it's C, triple bond C, and then whatever's on the other side, it's going to be a straight line. So it can't really, it doesn't want to do C triple bond like that because they're just too close to each other and there's all this empty space. So it's going to look like this instead.
You should see my face right now. Like, that was that. Like, damn, I was way off. All right, cool.
No, you were close. It was really close. But yeah. And then when it's drawn like this structure right here, don't forget that there are carbons at the beginning and end of the triple bond. So all those red marks are carbons. So there's 4 carbons in that straight line. But yeah. Let's see. Let's do number 5. So I want to give number 5 a shot. Let me see. How do I? Okay, there we go.
I think I'm almost confident I got this one right. Yeah.
Let's see.
Let me see. So I did 1, 2, 3, 4, 5, 6, 7,
Okay.
8, and 9. And then since it's dinitro, you want 1 on 2 and 3, so NO2. And then on 3, you want NO2. And then since it ends with a null on 4, so you'll have here O and H. That was mine.
What do you guys think? The jury of your peers.
Damn, you guys making me think I'm wrong already. Like, what I say.
No, I mean, it looks good to me. So we have that.
I think he's right. I'll just trust him.
Have trust. Have some faith. So let's see. Non indicates 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you got the 9 correct. For all. 1, 2, 3, 4. Looking good. 2, 3 dinitro. 1, 2, 3. Oh crap. Oh, double crap. Oh, sorry about that. Alrighty. So yeah, that was correct. Yeah, good job. I'm